Isotopes are variants of a particular chemical element which differ in neutron number. Although all isotopes of a given element have the same number of protons in each atom, the term isotope is formed from the Greek roots isos and topos, meaning the same place. Thus, the meaning behind the name is that different isotopes of a single element occupy the same position on the periodic table. The number of protons within the atom's nucleus is called atomic number and is equal to the number of electrons in the neutral atom. Each atomic number identifies a specific element, but not the isotope. An atom of a given element may have a wide range in its number of neutrons. The number of nucleons in the nucleus is the atom's mass number, and each isotope of a given element has a different mass number. For example, carbon-12, carbon-13 and carbon-14 are three isotopes of the element carbon with mass numbers chapter 12, 13 and 14 respectively. The atomic number of carbon is 6, which means that every carbon atom has 6 protons, so that the neutron numbers of these isotopes are 6, 7 and 8 respectively. Isotope versus nuclide. Nuclide refers to a nucleus rather than to an atom. Identical nuclei belong to one nuclide. For example, each nucleus of the carbon-13 nuclide is composed of 6 protons and 7 neutrons. The nuclide concept emphasizes nuclear properties over chemical properties, while the isotope concept emphasizes chemical over nuclear. The neutron number has large effects on nuclear properties, but its effect on chemical properties is negligible for most elements. Even in the case of the very lightest elements where the ratio of neutron number to atomic number varies the most between isotopes, it usually has only a small effect, although it does matter in some circumstances. Since isotope is the older term, it is better known than nuclide, and is still sometimes used in contexts where nuclide might be more appropriate, such as nuclear technology and nuclear medicine. Notation: an isotope or nuclide is specified by the name of the particular element followed by a hyphen and the mass number. When a chemical symbol is used, e.g., C for carbon, standard notation is to indicate the mass number with a superscript at the upper left of the chemical symbol and to indicate the atomic number with a subscript at the lower left. Since the atomic number is given by the element symbol, it is common to state only the mass number in the superscript and leave out the atomic number subscript. The letter M is sometimes appended after the mass number to indicate a nuclear isomer, a metastable or energetically excited nuclear state. For example, 180 meters 73 tar, radioactive, primordial, and stable isotopes. Some isotopes are radioactive, and are therefore described as radioisotopes or radionuclides, while others have never been observed to undergo radioactive decay and are described as stable isotopes or stable nuclides. For example, 14C is a radioactive form of carbon while 12C and 13C are stable isotopes. There are about 339 naturally occurring nuclides on Earth, of which 288 are primordial nuclides, meaning that they have existed since the Solar System's formation. Primordial nuclides include 34 nuclides with very long half-lives and 254 that are formally considered as stable nuclides, since they have not been observed to decay. In most cases, for obvious reasons, if an element has stable isotopes, those isotopes predominate in the elemental abundance found on Earth and in the Solar System. However, in the cases of 3 elements, the most abundant isotope found in nature is actually one extremely long-lived radioisotope of the element. Despite these elements having one or more stable isotopes, theory predicts that many apparently stable isotopes, nuclides, are radioactive, with extremely long half-lives. Of the 254 nuclides never observed to decay, only 90 of these are theoretically stable to all known forms of decay. Element 41 is theoretically unstable via spontaneous fission, but this has never been detected. Many other stable nuclides are in theory energetically susceptible to other known forms of decay, such as alpha decay or double beta decay. But no decay products have yet been observed, and so these isotopes are described as observationally stable. The predicted half-lives for these nuclides often greatly exceed the estimated age of the universe. And in fact there are also 27 known radionuclides with half-lives longer than the age of the universe. Adding in the radioactive nuclides that have been created artificially, there are 3,339 currently known nuclides. These include 905 nuclides that are either stable or have half-lives longer than 60 minutes. See List of nuclides for details. History. Radioactive isotopes. The existence of isotopes was first suggested in 1913 by the radiochemist Frederick Soddy, based on studies of radioactive decay chains that indicated about 40 different species described as radioelements between uranium and lead. Although the periodic table only allowed for 11 elements from uranium to lead, several attempts to separate these new radioelements chemically had failed. For example, Soddy had shown in 1910 that mesothorium, radium, and thorium-X are impossible to separate. Attempts to place the radioelements in the periodic table led Soddy and Kazimierz Fajans independently to propose their radioactive displacement law in 1913, to the effect that alpha decay produced an element 2 places to the left in the periodic table, while beta decay emission produced an element 1 place to the right. Soddy recognized that emission of an alpha particle followed by 2 beta particles led to the formation of an element chemically identical to the initial element but with a mass 4 units lighter and with different radioactive properties. Soddy proposed that several types of atoms could occupy the same place in the table. For example, the alpha decay of uranium-235 forms thorium-231, while the beta decay of actinium-230 forms thorium-230. The term isotope, Greek for at the same place, was suggested to Soddy by Margaret Tott, a Scottish physician and family friend, during a conversation in which he explained his ideas to her. In 1914, T.W. Richards found variations between the atomic weight of lead from different mineral sources, attributable to variations in isotopic composition due to different radioactive origins. Stable isotopes. The first evidence for multiple isotopes of a stable element was found by J. Thomson in 1913 as part of his exploration into the composition of canal rays. Thomson channeled streams of neon ions through a magnetic and an electric field and measured their deflection by placing a photographic plate in their path. Each stream created a glowing patch on the plate at the point it struck. Thomson observed 2 separate patches of light on the photographic plate, which suggested 2 different parabolas of deflection. Thomson eventually concluded that some of the atoms in the neon gas were of higher mass than the rest. F.W. Aston subsequently discovered multiple stable isotopes for numerous elements using a mass spectrograph. In 1919, Aston studied neon with sufficient resolution to show that the 2 isotopic masses are very close to the integers 20 and 22, and that neither is equal to the known molar mass of neon gas. This is an example of Aston's whole number rule for isotopic masses, which states that large deviations of elemental molar masses from integers are primarily due to the fact that the element is a mixture of isotopes. Aston similarly showed that the molar mass of chlorine is a weighted average of the almost integral masses for the 2 isotopes 35 Cl and 37 Cl. Variation in properties between isotopes. Chemical and molecular properties. A neutral atom has the same number of electrons as protons. Thus, different isotopes of a given element all have the same number of electrons and share a similar electronic structure. Because the chemical behavior of an atom is largely determined by its electronic structure, different isotopes exhibit nearly identical chemical behavior. The main exception to this is the kinetic isotope effect. Due to their larger masses, heavier isotopes tend to react somewhat more slowly than lighter isotopes of the same element. This is most pronounced by far for protium, deuterium, and tritium. Because deuterium has twice the mass of protium and tritium has 3 times the mass of protium, these mass differences also affect the behavior of their respective chemical bonds by changing the center of gravity of the atomic systems. However, for heavier elements the relative mass difference between isotopes is much less, so that the mass difference effects on chemistry are usually negligible. Similarly, two molecules that differ only in the isotopes of their atoms have identical electronic structure, and therefore almost indistinguishable physical and chemical properties. The vibrational modes of a molecule are determined by its shape and by the masses of its constituent atoms, so different isotopologues have different sets of vibrational modes. Since vibrational modes allow a molecule to absorb photons of corresponding energies, isotopologues have different optical properties in the infrared range. Nuclear properties and stability. Atomic nuclei consist of protons and neutrons bound together by the residual strong force. Because protons are positively charged, they repel each other. Neutrons, which are electrically neutral, stabilize the nucleus in two ways. Their co-presence pushes protons slightly apart, reducing the electrostatic repulsion between the protons, and they exert the attractive nuclear force on each other and on protons. For this reason, one or more neutrons are necessary for two or more protons to bind into a nucleus. As the number of protons increases, so does the ratio of neutrons to protons necessary to ensure a stable nucleus. For example, although the neutron-proton ratio are 3:2 he is 1:2, the neutron-proton ratio of 238:92 is greater than 3:2. A number of lighter elements have stable nuclides with the ratio 1:1. The Nuclide 4020 California is observationally the heaviest stable nuclide with the same number of neutrons and protons. All stable nuclides heavier than calcium-40 contain more neutrons than protons. Numbers of isotopes per element. Of the 81 elements with a stable isotope, the largest number of stable isotopes observed for any element is 10. No element has 9 stable isotopes. Xenon is the only element with 8 stable isotopes. 4 elements have 7 stable isotopes. 8 have 6 stable isotopes. 10 have 5 stable isotopes, 9 have 4 stable isotopes, 5 have 3 stable isotopes, 16 have 2 stable isotopes, and 26 elements have only a single stable isotope. In total, there are 254 nuclides that have not been observed to decay. For the 80 elements that have one or more stable isotopes, the average number of stable isotopes is 254 80ths equals 3.2 isotopes per element. Even in odd nucleon numbers, the proton-neutron ratio is not the only factor affecting nuclear stability. It depends also on evenness or oddness of its atomic number Z, neutron number, and consequently, of their sum, the mass number A. Oddness of both Z and N tends to lower the nuclear binding energy, making odd nuclei, generally, less stable. This remarkable difference of nuclear binding energy between neighboring nuclei, especially of odd A isobars, has important consequences. Unstable isotopes with a non-optimal number of neutrons or protons decay by beta decay, electron capture, or other exotic means, such as spontaneous fission and cluster decay. The majority of stable nuclides are even proton, even neutron, where all numbers Z, N, and A are even. The odd A stable nuclides are divided into odd proton, even neutron, and even proton, odd neutron nuclides. Odd proton, odd neutron nuclei are the least common. Even atomic number, the 148 even proton, even neutron nuclides comprise 58% of all stable nuclides, and all have spin 0 because of pairing. There are also 22 primordial long-lived even nuclides. As a result, each of the 41 even-numbered elements from 2 to 82 has at least one stable isotope, and most of these elements have several primordial isotopes. Half of these even-numbered elements have 6 or more stable isotopes. The extreme stability of helium-4 due to a double pairing of 2 protons and 2 neutrons prevents any nuclides containing 5 or 8 nucleons from existing for long enough to serve as platforms for the buildup of heavier elements via nuclear fusion in stars. These 53 stable nuclides have an even number of protons and an odd number of neutrons. They are a minority in comparison to the even isotopes, which are about 3 times as numerous. Among the 41 even Z elements that have a stable nuclide, only 3 elements have no even odd stable nuclides. 1 element has 3. There are 24 elements that have 1 even odd nuclide and 13 that have 2 odd even nuclides. Of 35 primordial radionuclides, there exist 4 even odd nuclides, including the fissile 23592U. Because of their odd neutron numbers, the even odd nuclides tend to have large neutron capture cross-sections, due to the energy that results from neutron pairing effects. These stable even proton odd neutron nuclides tend to be uncommon by abundance in nature, generally because to form and enter into primordial abundance, they must have escaped capturing neutrons to form yet other stable even isotopes. During both the S process and R process of neutron capture, during nucleosynthesis in stars. For this reason, only 19578 Pt and 94b are the most naturally abundant isotopes of their element. Odd atomic number 48 stable odd proton even neutron nuclides, stabilized by their even numbers of paired neutrons, form most of the stable isotopes of the odd-numbered elements. The very few odd nuclides comprise the others. There are 41 odd-numbered elements with Z equals 1 through 81, of which 39 have stable isotopes and promethium have no stable isotopes. Of these 39 odd Z elements, 30 elements have one stable odd even isotope, and 9 elements, chlorine, potassium, copper, gallium, bromine, silver, antimony, iridium, and thallium, have 2 odd even stable isotopes each. This makes a total 30 plus 2 equals 48 stable odd even isotopes. There are also 5 primordial long-lived radioactive odd even isotopes, 8737 Rb, 11549 In, 18775 Re, 15163 U, and 20983 Bi. The last 2 were only recently found to decay, with half-lives greater than 10-18 years. Only 5 stable nuclides contain both an odd number of protons and an odd number of neutrons. The first 4 odd nuclides occur in low-mass nuclides, for which changing a proton to a neutron or vice versa would lead to a very lopsided proton-neutron ratio. The only other entirely stable odd nuclide is 180 meters 73 tar, the only primordial nuclear isomer, which has not yet been observed to decay despite experimental attempts. Hence, all observationally stable odd nuclides have non-zero integer spin. This is because the single unpaired neutron and unpaired proton have a larger nuclear force attraction to each other if their spins are aligned, instead of anti-aligned. See deuterium for the simplest case of this nuclear behavior. Many odd radionuclides with comparatively short half-lives are known. Usually, they beta decay to their nearby even isobars that have paired protons and paired neutrons. Of the 9 primordial odd nuclides, only 147N is the most common isotope of a common element. This is the case because it is a part of the CNO cycle. The nuclides 6,3 Li and 10,5 are minority isotopes of elements that are themselves rare compared to other light elements, while the other 6 isotopes make up only a tiny percentage of the natural abundance of their elements. For example, 180 meters 73 Ta is thought to be the rarest of the 254 stable isotopes. Odd neutron number actinides with odd neutron number are generally fissile, while those with even neutron number are generally not, though they are fissionable with fast neutrons. Only 195-78 pt, 94b and 14-7n have odd neutron number and are the most naturally abundant isotope of their element.